Okay. So far we talked about some of the basics um, of neural networks. We primarily covered what convolution neural networks are and what recurrent neural networks are. We saw how to design some networks, run them in PyTorch and TensorFlow. So if you are completely new um, to all of that, then you might have some problems following along, because I'm gonna now get into more architecture specific scripts and things. But you should be able to like run the scripts for today's session, but you should go back through the slide deck. Last week we talked about natural language processing applications, um, and how the LSTM model architecture evolved into an attention-based network, and that evolved into a transfer neural network, which is now a state of the art. We saw some problems that come up while designing such architectures, and how we kind of solve those problems and build an end-to-end system. So I'm just going to go into computer vision applications this week. And if you haven't gone through the collabs or the tutorials, I highly recommend that you do that, um, just to have a more complete understanding of what we're doing. So we talked about before what convolution neural networks are. Um, I'm gonna go over that a bit. So we saw data sets like this where we had digits from 0 to 9, and that we needed to classify them just from this image. This is essentially a grayscale image, even though you see it in color. It's just a you all you need is a gradient from black to gray or black to white to understand digits. It's not so much um, for recognizing digits, you do not need colors. Whereas if you were looking at pictures of birds, then colors would be a very important attribute to look at. So you saw how we design convolution neural networks. We first looked at multilayer perceptrons, where we unfolded um, an entire image like this into one big list, where say each row of pixels was concatenated to convert the whole square into a list, and then we inputted that each vector position of that list as a input feature to a multilayer perceptron, and we learned the weights, and we did a classification, and we saw that for a simple data set like digits, even a multilayer perceptron does quite well. Then we looked at convolution neural networks. When you have more complicated image, and you need larger pixel intensity values to understand those kinds of images. So something like these, which are trucks and buses and cars and those kinds of things. So here color is also important, and also you need more pixels, more refined gradient intensity and all of those things to actually understand that image and train a network for it. So for this kind of an application, a multi-layer perceptron isn't a very good architecture, because then for every pixel you are making that into a vector value or an X. So if you had a 1024 by 1024 image, then that's a 1024 by 1024 long list, and each is an input vector. So that's just a large number of input features, and that input feature doesn't really capture any of the correlation or any of the relative information in that image. So whether a line or a gradient how that changes into another edge or another shape. You will not fully understand that kind of an information from a multi-layer perceptron kind of an architecture. So the state of the art like architectures are all based on convolutional neural networks for image processing and for any kind of image video kind of data. So what that in this architecture, what basically happens is that you would have learned this in signal processing, or if you did engineering and things like that. So basically, you pass an image through a filter. A filter is in this case also a 2 by 2 matrix, and it does a matrix multiplication operation on it where and you can define filters in specific ways. You can say you can design the filter as like 0 1 0 0, and that kind of a filter structure will pick out a line better. And then you can have another kind of a filter design which will pick out a normalized gradient better, a shape, a particular shape better. So essentially, if you have zeros and ones in your filters, you are doing a dot product, and so whatever value is there in a pixel gets multiplied by 1, and then whichever pixels are 0, then you don't get a value for it. So by manipulating what's in a pixel, so if you designed a uh, filter to have a shape of like a sphere or have a shape like a triangle, you just hashed out or masked out half of that matrix with zeros and the rest all of them are one. Then that itself is just saying that every time this filter passes over this image, it's only going to capture the left side or the right side of this image. So you can manipulate what information you extract from an image through these filters, and it's just essentially I'm going to zero out these pixels, I'm going to pick out these pixels, and how I'm relatively designing that 0 and 1 in a filter, I can pick out information of my interest, like lines and shapes and things like that. So once you do that, you design a network for that, how you can train a network that does this. If you had complicated images like this, you would pass that through a convolution neural network here, and then you would pool that information. So pooling can be a max pooling or an average pooling. So essentially, if you have passed a filter through an image, you have reduced its dimensions. You had initially 1024 by 1024, but your filter was 4 by 4. So from each a dozen blocks of 4 by 4, you are only picking one box through this max pooling or by average pooling. So for every 4 by 4 matrix, you can only pick one box out of it. So you are doing a dimension reduction, and through this dimension reduction, you are also picking out different kinds of features. So you do this process, and then you can train the weights of that network and how these features evolve, and what kind of features you learn. You can let that be determined by the network and self-learn that kind of thing. So when I said you can design a filter to have a triangle or a square or a sphere shape, what you ideally do is just randomly initialize these structures and then let the network learn through a process of backpropagation and through the loss function that what should these filters be, so that the end objective of classifying some images or of doing some particular task is met in the highest accuracy. So we are going to look at today how a neural network adapts these filter weights and what actually are the filter representations that it learns. And that's very interesting and also important to understand, because you can selectively use certain learned filters from larger networks to do specific tasks. There is a lot of pre-trained power in these kinds of networks, that we can like tap into and use for different things. So essentially, this is a training loop where you have an epoch, where epoch is a complete parse through a data set, and a data set is broken down into several batches. And what you do is you pass a batch of data through the network, then you like predict the label or the output of that network, and then you say, and this prediction is a soft prediction where it's not just if you had a class of 0 to 10, you're not predicting if it's 0 or 10, you are predicting a probability of 0 to 100%, or a ratio from 0 to 1 of this thing being 1 or being 9 or being 7, something like that. And then you take these soft probability kind of things and take that against the actual label, and then you calculate a loss, so how much you got each of those things wrong. And then from that loss you have a scalar value, that's just one value at the end, and then based on that you can take partial differentiations and back propagate those differentiations and update the weights. So essentially, your y is a function of your weights, and your loss is a function of your y. And so from that weight loss output, you can get a delta loss per delta weight, and that's your partial differentiation. And then you can update your weight with a delta weight, which is computed through the back propagation of this loss. So hopefully by now, when I'm telling you this, you can see a mental image of what I'm talking about, and that this part is like well ingrained from our previous discussions. So that's essentially what we're doing. We in a convolution neural network, we just do a feature extraction kind of a process, feature extraction kind of a process, where we extract important features from an input, and so that we have the most accurate and most relevant information for a particular task. So now we are going to look at um, these were from previous tutorials, this convolution neural networks script. And today we are going to look at first how a
Is that okay to
convolution.
ask you questions, or would you prefer if we wait till the end?
Yes, it's okay to ask, but maybe I can answer in batches. Did you have a
So,
particular question?
yes, I had a quick question. When you were computing a loss, could you clarify how the loss is computed in case of classification? It's a little bit more clear in case of regression, but in case of classification, how would one go about computing a loss function?
Okay. How about we kind of covered this quite a bit in the previous sessions. How about I keep that question for the end and I can kind of go over what we did before.
That's fine. Could you just say like what values do you use for computing the loss?
So you
It's not an
predict.
expression problem, right? It's a classification.
Yeah. So you predict you have, so if you had 10 classes that you needed to predict, your final layer has 10 neurons, and they give you a softmax output of whatever the weights that were coming in. There's a function there, and it's a softmax that it assigns a 0 or a 1 to each of those nodes, and then you have a 0 and a 1 actual label there. So that when you have that activation coming in, you have a soft assignment which is like a logarithmic probability, and you take based on your loss function that you have used, you take based on an entropy or a negative log loss, you do a computation of this softmax output of those 10 layers and what the actual output is. So the actual output, you know, it's a 0 or a 1 for each of those classes, and then from the softmax activation you get that value, and from that difference you can compute a loss. It's not very different from a regression, it's just you use a different loss function to do that computation.
Okay, so you're using the numerical values of confidence, basically, right?
Yeah.
Thank you.
Okay. Yeah, we can probably go back to those slides at the end if someone wants more clarification. So here in this one, we are looking at, okay, so let me start with transfer learning. So last week when we talked about natural language processing, we saw how these transformer networks are pre-trained on a lot of data and a lot of text. Um, and we take that kind of a model and fit that or fine tune that on a particular task, or we just freeze that network and add additional layers so that we can use the weights of that model to do a particular task. So a very natural language processing is using these transfer learning concepts in very recent development. It's only been like a year or so that this trend has started. But in image processing or computer vision, this has been the norm for quite a while. And so if you have what you did last time with convolution neural networks and the kind of accuracy that you got, if you have a more complex data set, if you have a lot more classification labels, or if you have a data set that does not have a lot of training data, but you need to do a lot more complicated work with it, and it's not just like classifying digits, but you have to classify like 1,000 categories of objects, products. Maybe you have like an Amazon kind of a system where you're automatically classifying the inventory or something like that. So that kind of a task, if you do not have millions and millions of data points, you cannot really use or build a CNN from scratch. And then even if you did build a model like that, you would need huge amounts of resources to train something like that. So the convention is to use pre-trained models. There are several pre-trained models now, and it kind of started with an ImageNet competition. I have left important links here and in the presentation that you can go through. But essentially, what's happening there is you had a huge data set that had like 20,000 images, 20,000 image labels, and then you had like millions of images for those labels. And then a huge network, VGG, was trained on that. And each network has its own kind of special architecture that all kind of is derived from this convolution concept. So here you have the VGG16 and all the accuracies and the number of parameters are shown. So you can see that the initial model was a really big model with a lot of parameters, and it had a 0.9 accuracy. But then you have but a smaller network is doing better, and now you have even smaller and more like pruned networks. We haven't really talked about pruning, but pruned networks that does even better now on specific tasks. So here, how it started, it was like the same convolution layer kind of a concept, but making it more deep. So adding more and more number of convolution layers in that model. That was something we built on the first class. And then AlexNet was something deeper. And the concept here was that if you have a task which is very similar to a task on which this big network is trained, then you can use this whole initial pipeline, and then you can change some of the last layers here to like fine tune these weights only for a particular task. And but if you have something a different kind of task, and that was very different from what this was trained on, then you have to kind of figure out which weights to keep, which layers to not use, reinitialize, and things like that. So that is where visualizing networks and what they have learned really becomes useful. So in this kind of when I mean different tasks, like say if this thing was trained on a lot of images of different kinds of categories, uh, and your task is a classification task just like theirs, then you can use this network in initial architectures, but instead of having 10,000 labels, your particular task maybe only has 4 labels, so you can change the final layer of it, and just retrain these weights to get that final classification. Um, but and you can like freeze the rest of the network, or you can also fine tune the rest of the network depending on if you have enough computation and things like that. But if your say task was to generate images, or to superimpose different kinds of images together to create artistic representations or things like that, or add distortion to an image to get some kind of an effect, then you cannot really use the all the model weights the way they are. But you can inspect a pre-trained model to see if it has certain filter weights, certain kind of things that you can reuse, and reinitialize the rest of it, or change the architecture, and things like that. So in reusing transfer learning paradigm, you have those kinds of two concepts where you use all the model weights to do a particular task, or you use partially something to reuse features that it has learned from a lot of data points. So Inception Network was quite famous for a while. It did better than the previous ones. It had a more complex architecture where these inception blocks were had these convolution nested networks, and it kind of looped back into its self learning kind of embeddings. So it was it you can read more about this, but it kind of learns embeddings, and embeddings uh, are relearned many times, and mapped back, and that's why it's called an inception network, to have that kind of a nested representation architecture. So yeah, so you have different kinds of models, more complicated ones, more deep ones, and depending on your kind of application, you can look at the different uh, weights and things like that, and we're going to see how to do that, and build an application around it. So for a visualization, here the objective is to see, for each kind of filter weight, what kind of an image would actually activate that weight the most. So this is kind of a different reverse way of thinking about it. So let's say when you had an actual image that you needed to learn and come up with a label for it, you passed those images through that network, and the weights were learned, and you finally had a loss, and then you back propagated that loss, and hence you updated your weights. So what actually happened is that when for each kind of image, or for your data set, whatever images there were, and the loss that the relationship it had with the labels and with the loss, through that back propagation process, certain weights just learned better. If you looked at the learning curve for each weight, how many times it was updated, what kind of an update it was, how many iterations did it continually update, did a weight stop updating after a point, and while the rest of them kept on updating, was one weight never really updated, so it was really insignificant for the actual learning process. So you are not really learning or seeing that part when you are training this model. But here the objective is, you can say that, okay, let me give a loss function or a loss objective here, that what is that image that would have created the highest activation of this weight, or highest uh, change in this weight overall. So that's what this kind of an exercise is doing. You have um, this resonate 50 model. You can upload that from Kiros's model layer. It will have all of the pre-trained model weights and things initialized for it. So for this one, you get the layers, you take the model from Keras, get the layer weights, and you extract the model features from it. Then for the loss, you are just defining an activation through the feature extraction, uh, and you're saying give me the mean. So reduce the mean as a negative objective. So you want um, something that gives you the highest activation. So you can say a gradient ascent or a gradient descent. Usually you have a loss, so your objective is to minimize that loss, but here you want to see which is the highest activation, not the minimization of the loss. So here it's a gradient ascent. It's just based on your objective, what you're trying to do. You change this structure of the problem. If your objective was to have the minimum value there, then you do a descent. If your objective was to do a maximum value, then you do an ascent. And you can do this for other kinds of problems as well. But here you are defining a gradient ascent kind of a structure. Then you're randomly initializing a image for which this would have created. Your hypothesis is that for this randomly initialized image, I would get the highest or the maximum loss. And so you train this, and then after you have trained for a certain number of epochs or iterations, then you visualize the image that it has learned. If you do that, this is what you come up with. And I really recommend everyone to like do this exercise. And there is another script also which does a very similar thing for a different network architecture in the GitHub repo. So you can look at each filter. So in this block, it's doing this process for each of the filters, and it comes up with this kind of a representation. So here you can see what are the kind of shapes and structures each of those filters has learned. And these are mostly like voxels or more kind of mathematical representations of structures and numbers. If you have uh, um, sorry, so why look only at the highest activation as opposed to the top two, three to understand what may lead to the edge cases that sway the model's results? Yeah, you can do that. Yeah, we can discuss this more in the end. You can, and this is none of this is really a hard coded or a very factual thing. It's a very soft kind of or a probabilistic kind of way of looking at things. So sometimes a lot of these links, if you go in depth to their connections, people have discussed these things, that if I actually give an image of a bird versus a fish, which are these filters that actually will be most influensive in coming up with the right prediction. So none of these filters actually have a representation of a bird, or of a animal, or of any particular thing. So that was kind of initially the assumption people had, that maybe some of these filters are learning a structure of a bird, and some of them are learning a structure like a house or tree, and so it just knows to distinguish, and those particular weights will get triggered, and you will come up with the outcome. But it is not so hard and fast kind of structures that it learns. If you look at some of these patterns, some of them look like fuzzy patterns, like feathers. Some of them look like more like kind of triangular shapes, kind of replicating skin textures, and those kinds of things. And so these kind of learn the numerical patterns of things. So if say a particular image, the way the texture of that skin color, or of that gradient of that hair, or of that feather is laid out, how those numbers are actually related with each other, that's the kind of representations it learns. So sometimes it comes up with circular things like this, sometimes it comes up with like rectangular structures, and some ones learn diagonal representations and things like that, and it's not really um, something you control. But and they all of them have various degrees of things that it learns. If you take away a particular degree of information in here, you will probably see like less hard lines, or less colors, or more of a grayscale representation. So you can take these images also can have different filters and different levels of information. So it in how people analyze these kinds of models is they look at these weights, and then for a particular data set they pass through them and see which of them they capture the activations, and see which weights are actually getting more activated through this process for a given data set. And it's a process of pruning, or fine tuning a model, and there is more literature there. Next week, I'm going to talk about how to prune a model, and then I can talk more about that. So essentially, that's what this is just learning voxel-like representations of numbers and patterns, and then you can reuse, like a lot of applications can actually use some of these filters to impose certain attributes. If there are two kind of filter weights that have learned one kind of representation, and the other one has learned the other kind of representation, you can merge those filter weights to create a filter or create a effect of an image. So there are many sorts of applications of these things. Um, so now we look into how you actually can use or reuse a pre-trained model architecture for a specific task. So here we are going to use a couple of different models. We are going to start with ResNet, and then we'll try a bunch of others. Um, and so here it's a bit of a discussion of how the different constructs work. You can take if ImageNet is a pre-trained model for that looked at a classification task, and this is actually the base of all transfer learning techniques in computer vision, or most of them. So you have for a particular classification objective, this model learned features from image data, and then learned how these different representations go together. and then it kind of learned this map in its network where this activation when happens together, the probability of this being a dog is higher than when the probability of that being a cat. So it learns that kind of a map. So you can have a very similar kind of an objective where you are still classifying things like dogs and cats, but maybe instead of having 10,000 classes, you have a smaller things that you need to do. Maybe you need to classify which breed of dog, or if this is a cat or a lion or a panda or a cheetah or different kind of cat families. So more specific tasks that is not so broad as what it was pre-trained on. So the task is still similar, but you can now retrain this model or fine tune this model to for that specific task if you have enough data points for it to have a fine tuning effect. So here we are looking at a data set which has a, a distinction between ants and bees, and this is a very kind of a difficult task and important one as well. And how a lot of these applications evolve is through different kind of people who are interested in these areas. Right now there are many papers and discussions on how to separate different breeds of dogs or separate different kinds of skin diseases, different kinds of lung diseases. So those are very fine grained applications of a particular thing, and so doctors or anthropologists or different kinds of people are interested in them, and so data scientists in those areas develop specific models for that kind of stuff and specific data sets for that kind of stuff. So this one is a distinction between ants and bees. Like ants are more pests. You may want to kill ants in certain points. You never want to kill bees. So that distinction is very critical if you're going to take a decision based on that. So for that, we can use some of the pre-trained models, but then we have enough data on this kind of segregation of the two kinds created by these domain specialists, and then we can fine tune that model to classify this to the highest possible accuracy. So I really suggest you do this now. I am not going to run it because then that would freeze my system. I did this already this morning. Here there is a tutorial for it. There should also be appropriate links to collabs. If you have taken a clone of this repo, then each of the things will either lead to a tutorial or lead to a collab. So the collab ones you can run on cloud if you do not have a system set up. But hopefully by now everyone can run this on their local. So here you're taking this data sets, you are applying transformations to it. We have talked about this before, but we want to standardize all the images to a certain shape. We augment data sets using different kinds of techniques. If all the images are horizontal or of a particular angle of the thing that we are classifying, then we can augment that using rotations, flipping them along an axis, of scaling like differentially within an image. Um, so we can use different kinds of techniques like that. We can crop images. So if an image is like to the always to the left of the screen, so say you used a camera to record bees, and how the camera was positioned to a flower, the bees always come to the left of that image, but you do not want that to be trained, that's the only data that the model sees, because then it will have a huge bias. Anytime anything is on the left, by default the model will try to predict that as a b. That's just how models work. If relative information of a particular thing has a very strong bias, then models learn that bias very very well. So it's augmentation is the way to make sure that you do not have such biases in your data set. And most of the times, if you're trying to build applications, for projects and stuff, these are the kind of considerations you need to uh, take into account. So here we do all sorts of transformations to the image. Then we normalize the scale, the color, the gradients of that, and these are all RGB images. And then we finally come up with the data loader. So we talked about this before. Torch has, when you training the model in PyTorch, the PyTorch model expects a data loader object. So you have to convert your data, be it in a NumPy array or however you got that data into your notebook or your system. You need to convert that finally to a data loader. So you might have to rewrite some functions depending on what kind of data you have. Or you can use these PyTorch kind of defined structures of defining transformations and defining data loader methods for it. So you give a data loader a path or a set of images from NumPy arrays, and it will create that object for you. So device, if you have CUDA, an NVIDIA GPU, then you use CUDA, or if it's not available, it's a CPU. This is a convention of assigning a device. Then this is just to visualize. You have to make sure that they're all the same size and proportion, um, and visualize that in a grid, and then you train the model for it. So here, instead of defining the entire model like we did before, we are now going to use the transfer learning approach, where we are not going to define the forward function with the convolution neural networks like we had done before. We are going to use the model, a pre-trained model and its weights. So here, I can pass any model that has from pre-trained or a those kinds of operations predefined on it. So if it is like your model file was saved in TensorFlow or in Thanos, and you're trying to do this in PyTorch, then you might come across some problems because that model needs to have some metadata structures and things like that. That this then when it loads up, then this data loader and stuff like that is expecting. So those kinds of things you have to make sure, like the state dict, this should be defined in that model. So there are libraries, and PyTorch and TensorFlow give you ways of converting models from different libraries to it. So you can do that if needed. But here the model we are going to use comes from PyTorch, so we should have all of this defined in there. So we take that model, and from the state dict function on it, we get all the weights, and we get the labels. So this is this layer. The layers is name is this, that's the weight for it. So we get the full metadata information from this um, state dict function, and then we can and how this is just loaded up, it always going to give you the best model weights for which it had got the best validation accuracy previously when it was trained. And the model files all have all that metadata in there, so you are going to load that up. Then for you need kind of need to set the model in a train or an evaluation mode. So when, like we did before, that when we were training the model, we could update the gradients, but when we were evaluating it, we said no gradient, or torch no grad, or we did that in a block of code where we were not updating the gradients. So here, because we kind of have are not defining those functions ourselves, it's internally in the class structure of the pre-trained model. So we can set those kinds of gradient on off things similarly like we did before, but through these function calls, where when we set the model dot train and model dot eval, we are just setting the all the gradient, all the frozen or unfrozen. So yeah, this is not, when you say model dot train, you are not telling the model to train, you are just setting a mode of that model. So from that data loader, you have the batches, you have the inputs and the labels for each batch in that data loader. You take them to your device, if it's a CPU or a GPU. Then you are doing the optimizer no gradient, so you're zeroing out all the gradients that it might have had from previous training iterations. Then with gradient enabled in the training phase, you are updating the loss function for your particular input data set, and you're updating the weights. And in this case, you are updating the weights of your any specific structure or that you may have added, or you are doing it for the whole network. So in this case, you can see that you did not do anything extra to this model. You did not change any layers, nothing. You just have the architecture is the same. The initial point of this training was where it was left off from a different objective. You are now just updating those weights for the current data set. So you are going to same go through this for epoch, evaluate the loss function, then the backward and the optimizer step, um, and you calculate this loss, the same thing that you did before. Um, then nothing about this changes. You do the validation and the prediction, you compute the accuracy, you can compute the matrix, the confusion matrix for it, um, and then you can try out different models. So here you can say ResNet, or you can say some other pre-trained model. Uh, this will have options like AlexNet. So AlexNet is an option. You have a bunch of options there. And so you can take the model and send it to this function here, pass it in, and then train or fine tune that particular model with this data set. So here, same thing. This was you had to send your loss function, your criterion, and these hyperparameters. So you defined that your loss function was your cross entropy loss, and you use the um, SGD optimization. So yes, for the data set, um, you need to download that. So this is from the tutorial, from the documentation. This one tells you you can download the data from here. So when you do this, when it will, hopefully you can see my screen, it will download this zip folder. So you need to now unzip that and put that in the directory. So that's what I did. I downloaded that and now it's in my directory, or you can give it the path that you want for this folder here. Um, or with a folder rate, and then so you have now control over the hyperparameters still. You can say that instead of SGD, you can use an Adam optimizer, you can use a different learning rate, or you can use an RADM, or any number of epoch and things like that till you get your desired performance for this particular task. So you can train this with different kinds of models, and compare which pre-trained model gave you the best result. I did a couple of comparisons for a feature extraction task. So in a feature extraction task, that is different from a fine-tuning task where you updated all the model weights. So you had control over the original model. You could just reuse all of its weight, and like if you had a different objective, not just bees and ants, if you had like 10 different varieties of bees and 10 different varieties of ants, you would need that much amount of data to have that kind of a distinction between them. So you need more data, the more complex task that you have in mind, and then you need more training cycles and more training iterations, and you can play around with these hyperparameters till that big model does well for a more complex task. But the other approach is to use this pre-trained model as a feature extractor, where you, independent of what was your objective, you are going to use the model's weights or its pre-trained functionalities as a black box kind of a thing, which just has these features, and you do not train that. You just train either a particular linear layer that you add to it, or you fit that block into a bigger network that you create for yourself. So here again, you are loading up a ResNet model. Here you can use GoogleNet. You have a lot of options uh, that this comes with. Um, and so you're setting it pre-trained, you're loading the whole model, you are setting all of the parameters in this model that requires gradient to false. So anything in the iteration process, you are not going to update the model in any way. So here then you add um, requires gradient. Modules have requires gradient by default. So the linear layer that you're adding to it, a fully connected layer, that will have by default the gradients are set to be true. So anytime you declare a new layer or a network module, in by default it initializes the model weights, and it has the requires gradient set to true. So similarly, now you are setting that to a device. You are defining a loss criterion, optimization function, parameters, and now you are stepping through the process and doing the training. And you can do this in different kinds of ways. You can, uh, you know, have a small data set, like a few epochs, And so the kind of model architecture, what kind of parameters to freeze, you can tweak a lot of this. And we're going to see an example of meta learning, where this kind of a concept is taken a couple of steps further, where you do not need a huge data set or a big enough data set to use these model weights. You can give it a paradigm or a kind of a structure where you just give it a few examples of something, and just from previous knowledge or doing things, it learns to do a particular special task. So here, you could have also, instead of setting requires gradient to false for all the network parameters, you could have put a condition saying that if the architecture started with a convolution, the name started with a convolution, only then I am going to set that to false. So you're just freezing the convolution network, keeping the rest of the dense layer networks layers updatable, or the other way around, where you kept those layers fixed and updated the weights and the embeddings of those. So you can play around with that. We kind of did this last week, where we only froze any weight that started with BERT. So you froze the transformers weights, and you did not update that, but the rest of the architecture you could update. So you can play around with that for a particular application, and see with different changes, how does that model accuracy improve. um, and so trying out different pre-trained models, different kind of strategies for doing that, you can try it. So just show you, hopefully nothing is running right now and this will not break anything. uh, okay. So when you do this named parameter instead of the parameters, you can do this as well, and say if my param 0, so each of these are um, a tuple. So here this is telling you the name of this. So you can say that if my param 0 starts with convolution 1, then only set that requires gradient to false. Or it starts with inception, then set that to false. You can do stuff like that with it. And then the corresponding weights, they will either update or not. So a lot of specific application tweaks with these kinds of settings to get improve their performance, and that's a lot of the times, that's what people do. If you have a specific application and you acquire a data set, you do these kinds of experiments and compare accuracies and how well a model is training and things like that. Right. So we're gonna look into some more advanced stuff that we can do now with 3D data sets, and 3D convolution neural networks. Um, but before that, it'd be good to look at a meta learning application, which is the same or a very similar concept to transfer learning, but it's actually very different theoretically. So when you have um, a kind of a problem formulation where you have a lot of data, and you have a particular task in mind, and things like that, then transfer learning techniques gives you eventually better results and faster results. But then there might be many occasions where you do not have a ton of data for something. And so this is the link to this collab. Um, and there is also another one in the GitHub repo, that's the Siamese network. So these are two meta learning kind of applications. I'm just gonna go through this one. So here, this data set is essentially looking at digits and letters from different languages, and that's why this is called omniglot. uh, it's being able to recognize digits and characters across many things. Now, if you have a network that has learned to recognize shapes and images, and if you have a network that has learned to um, differentiate between text of different kinds of things, and in general it had a very broad objective, um, then after that kind of a trained model is there, you can fine tune a model in a different sort of a way, where you are just changing the embedding structure um, of a learned model so that it does well on a particular task. Um, so the presentation should have links to more in-depth discussions. This is a very active area of research, and it's you don't need to understand everything to use it, but uh, essentially what this kind of structure says that, um, say I have, so how does the human brain work? I have learned to do a lot of tasks. I have learned to read books, like storybooks, then normal curriculum books from all my schooling. I've learned to read mathematics to physics to chemistry, and just by looking at how the kind of keywords that gets used in a particular domain, I would know if this topic is chemistry or it's talking about math. It will, even though there might be overlap between the topics, but I would have, from a lot of years of conditioning and training, would know that okay, if the primary concept here is carbon structures, then this is probably chemistry. And if the primary structure here is about atomic strength, this is about physics. But if it's talking about floating point numbers and about uncertainty and probability of some atom being a carbon atom or hydrogen or things like that, if it's more talking about the probability and the numerical aspects of this, then it's talking about the math. And usually a lot of the concepts that are there is a mix of various topics put together. Even in like newspapers and stuff and storybooks, you can have different genres of information mixed together. When you're talking about a sports broadcast, you're not just talking about a sportsman or one particular player. You're not talking just about the audience or the spectators or just the weather or the field. It's a composition of a lot of these things that happen together. Now imagine if a network is trained on a lot of articles or a lot of images of people playing a sport on a field or something like that. Um, then it should have learned inherently the concepts that there is a field, there is a player, there is an audience, there is a ball, there is a score system, there is a goal, and all of those aspects. But then there is a more complex interplay between all of these things that give you an outcome. But if you have a broad kind of a structure like that, then can I reuse that learned thing to do then a particular task, and that for task give it only very specific examples. So now if somebody tells me fill in the blanks in a crossword puzzle or something like that, I don't have to be shown what that fill in the blanks task is. I do not need to have to be like shown how to fill a crossword puzzle. I know them. But if there was like a new type of game, like a different kind of Sudoku, then maybe someone needs to show me an example of how this box needs to be filled for me to start playing it. So I know the logic for doing something from previously having done crossword puzzles or having solved jigsaw puzzles and those rudimentary things that we do. But for a very specialized task like doing a Chinese checkers game or something like that, I will probably read the instructions or the manual to see what are the rules of this game so that I can start playing it. So meta learning kind of looks at that concept where you don't need a whole huge set of examples and it's not a fully supervised construct. You just give a problem certain examples of what needs to get done for a certain thing, and then um, the model from previous learned examples from its broad perspective of things should be able to adapt to this. And this is a very interesting area of to look at, because more and more we all the kind of applications that have a very set domain, people like Facebook and Google have those kinds of data sets and have marked those fields with benchmarks and with this whole set of tutorials and resources that you can if your objective was to do those things like these kinds of tutorials and stuff that we're doing now, it's very easy to do this. You do not have, and then you probably just need to start collecting images with your phone, or build an application layer for this where anyone can take a picture from the phone and integrate this model to a system and to start using it. But what if it's a kind of a task that people haven't really figured out yet? What if it's something that you cannot collect a lot of data from? Mining applications, for instance, like it's very difficult to get particular images of all the sorts of things, and to build something from scratch over there would be very difficult. And also the kind of tasks that need to distinguish between certain set of things, like more fine grained distinguishing between is this a cheetah or a tiger or a house cat. So those kinds of applications you wouldn't like need a lot of images from scratch to train a model from scratch. But instead, if you have a model that's been trained on a lot of that kind of thing, then you can just update for a few iterations with a smaller data set, and that kind of a thing is called few short learning. So you're just kind of shifting the embedding of that model um, to do a particular task. And to understand that concept fully, you would have to understand the network and what that embedding and what of these filter layers are learning and all of that. So you need to do more of that hands-on. But essentially, when you have, say, a sentence or a word, you have an embedding for it in that meaning space where all these different words that are very similar in meaning, maybe across different languages that are similar in meaning, have formed a sort of a cluster. And then these clusters, when a dozen clusters of words are together, they form a particular domain of sentences that you can assign a topic to. Similarly, for computer vision, each image, when it's broken down through those filters into features, each image then is just a composition of features, and that features have its embedding through that process of how those convolution neural networks updated its weights. So when you have this distribution of numbers, essentially it's all a distribution of floating point numbers, and they know how these voxels are going to be formed and what this set of voxels are embedded to in terms of an input, it's a preset kind of a structure there. But if you have a smaller set that's very task specific, you can still shift that distribution to a satisfactory degree for it to then specialize to a particular task. It is not very analogous to how the human mind works, but it gets pretty much the job done in the current state of the art. So you can shift those embeddings and the probability or the dependency between inputs and outputs, and so that the current, when you leave this current model, it's shifted to a certain way, that it now knows how to do this particular task better than it did from a vanilla state. But if you had not given it those examples, then it would not know how to do this. It would uh, it wouldn't know that there is a particular task here. If I had trained my model to classify 10,000 categories, any kind of dog image I give it, it does not understand that this is a dog image already, and I'm just trying to classify the dog image into what breed of dog it is. It understands that my objective here is to classify what animal this is or what object this is between all the things that I know. So that's how the model will look at it. But the moment you give it this kind of a meta learning wrapper to it, then it knows that, okay, my objective no longer is to predict if it's a dog. It's just to predict a fine grained structure of what are these dogs I have seen before in when I was pre-trained. And so all of these dogs were small, were cute looking. All of those dogs were like big and angry looking, and other dogs were like these very pet and always had like a park or something like that in the background. So there is a kind of a grouping of these kinds of things that is learned, and from this shifting of this embedding, it knows that, okay, I have now been shown four types of images for particular breeds of dogs, and I'm going to try and find in my embedding space which the things that I have been given recently, which are the ones they map closest to. So it groups them or soft assigns a cluster to these objects. And so now in future iterations, when you give it unseen data, it just tries to map that data point to the grouping that it has seen. And the examples that you give it during that meta learning process, it just uses them as kind of like a reference point to know that, okay, these clusters exist. So there was this cluster that existed, and that was the label that I got from this kind of an example. So I know now that there are, so in a coordinate system, now I know that there is a coordinate point of 0 0 and another coordinate point of 1 0, and so I know these points exist, and I'm just now going to map any unseen thing to these coordinates as the closest embedding of features that I can find. So that is the kind of thing we do for meta learning in a very broad perspective. This field has like really a lot of potential when trying to build very novel kind of applications. And when you do not have data sets and things like that readily available, it is now the go-to method to try and solve a new problem. And so in this one, this omniglot data set, you have different digits from different languages or different characters from different languages, and you are going to give it some final examples to do a classification task. Um, you can try and run this. Yeah, and maybe if there is like any questions or doubts, we can talk about it next week. I'm going to look at pruning and meta learning more objectives next week, and then maybe we can have a more in-depth discussion about that. So yeah, this is another network that does the same thing, the same omniglot data set, go through these two, and I'll try to find some more resources to explain this stuff a bit better. So we're going to look at 3D data sets and video processing applications. Um, Okay, so here there is a question that if in the pre-training it did not see bees and ants in the pre-training process, how does it do that task when it has only seen cats and dogs? So the first rudimentary answer is that uh, all images are images. At least it knows that this is not a sentence. It's not a text. It's an image. So from pre-training, at least it has that starting point. Then it knows that okay, there are animals with fur, animals with hair, animals with four legs, with two legs, with different facial features, eyes, colors, shape, relative shape, and then there are things like also like background. So if you have a lot of bee images, it's likely it is in a garden on top of flowers, and similarly ants will also have similar backgrounds, but dogs and houses and things like that will very different backgrounds and very different biases. So at least then it knows okay, that I have seen all of this data, and I so know what hair, those voxels for hairs looks like. So I have at least the building blocks of separating different things into different groups. I know all of these animals had hair on it, so at least there are four filter weight activations that are going to go off when I have that kind of an input. And so it has those building blocks. Now it's experimental. If you have data, or if you had a pre-trained model that had a data set with bees and with ants in it, you can use that and compare that. If I used this model that has previously seen it, does this does better on a particular fine-tuning task, or the difference is insignificant. If you do not have a task or a model that was trained on those two classes, can you then add those two classes to the bigger data set, and fine tune that model for some time, and then fine tune it again for a particular task that you have right now. So you will have different options of trying trial and error before you know which kind of a strategy of training gave you the best performance. And now there are things like computation and those kind of things that come into the picture. If you have to update a VGG model with huge data set, you may not be able to do that with your computation power. Then you can say that I'm going to just add the bees and the images, and if you had say 200 images of each, you can add that to a data set of 200 images of dogs and cats and things like that each, and then make a well distributed uniform label smaller data set that has the different categories, and then just fine tune that pre-trained model with all of those categories, and then fine tune again on only those two specific classes. So there are many different possibilities you can try out. Um, and usually like there is no like set formula for it. If the pre-training had things more like mechanical objects, like had houses and cars, and all those kinds of images, it is quite likely, just from a naive perspective, you can think that it is more likely that that kind of a trained model will do worse in this task than something that had insects and birds and cats and dogs in its training, because at least it has human features or animal features and those kind of features of objects that it has learned. Whereas the, like, if something has only seen trains and cars, that the features that it would have learned would be very different. It would not probably have learned rounded objects at all. Most mechanical objects are very trigonometric shapes. They are very like edgy. So probably that model understands edges very well. It does not understand rounded structures, furry structures, fuzzy structures. So just from that perspective, you would know what kind of a pre-training model to start with. If you have that information, and then you can try different strategies till you get a desired performance. Um, yeah, so I mean, why the features of a different class are useful, because if you do not have that final layer in this task, you do not have that final layer. Your final layer is your task specific. So in the rest of the model doesn't know until it came to that layer. There was no concept of these classes. It was not something that the previous layers cared about. What the previous layers knows that there is a loss and an update, so it knows that to the next one, to get a more accuracy or to get a better feedback, how do I need to update something? So the previously trained things and the convolutional features or whatever it has learned, it did not know that what it was learning. It has just learned these rudimentary features from it. And so when you're composing, and the pruning and the reducing weights goes back to these things. So a lot of these weights don't update or don't actually matter when you are doing a particular task. So for when you do a particular task to train models faster, you can remove those weights. So but for that you need to be able to analyze the model through these visualizations or through other techniques. And go through the process of which kind of data set and what kind of model architecture had the best weights and best pre-learned features for a given objective now. Okay, so moving on, we're going to look at some 3D data sets. And I haven't really looked at the presentation much, but so the meta learning tutorials are here. We're going to talk about more about this next week. And then this is the okay. So for the next week's session, we probably gonna have more like a video processing application built and deployed kind of a thing. That's the objective. So it'd be great if you can try and look at these tutorials and try to build something yourself. That will give you a better understanding of what's going on. So here now, for point clouds or for 3D images, things change a bit. So when you have so I'm going to answer the questions at the end. Hopefully this is enough. We have 30 minutes to finish this. So when you have images, you have um, a grid. You have an XYZ coordinates. You know what's the starting point, what's the end point. If you have a 3D image, that concept kind of changes a bit. A 3D image is essentially a group of activated points or pixels in a box or in a sphere, in a volume essentially. So a volume doesn't necessarily have a starting point or an ending point, usually you define 3D coordinates in terms of an axis. So if you go back to your geometry or high school geometry, you would have a coordinate system with your XYZ where you can place things, and then you have a circular coordinate system where you define things in terms of axes and rotation about axes. So you have that kind of a representation for 3D objects. And so how do come up with model architectures and define these kinds of convolution kind of architectures or ideologies for that kind of a data set. Um, so here, PointNet is a very good example. We are also going to look at a 3D CNN. Essentially, when you kind of have to go back to how 3D points are collected, and how this field is moving forward. 3D really is um, the future, because right now all the mobile devices, all of those things have the ability to capture uh, the objects and things in 3D, and it has more information embedded in them. And so if you can leverage the ability to take a 3D image of something, you should use that power. And so the field is really moving towards point clouds and 3D structures, and more so with the augmented reality VR kind of applications. There's a lot of development here. So in a say if you were taking a video and you had an object moving from in a space, you could capture that in a video, and from a short video clip you could actually resegment some an object into a three-dimensional object instead of taking just a picture of it. So is similarly, I don't know if anyone of you have ever tried HoloLens or any like headset that does VR stuff. So anytime you do have like a HoloLens kind of a headset, it what it does, it takes a spatial mapping of your surroundings. It goes and creates a point cloud kind of a memory map, so that then it knows in this area your hand or a gesture of your hand, it has reference points to understand that motion in that space. So creating 3D point clouds and pixels and voxels and those kinds of things, its own kind of area of engineering. But essentially, what you do is there are two kinds of main ways of doing it. You can create voxels um, where you have points connected with lines or edges, and so how your computer, let's say, displays things, it's always in terms of triangles or quads. That's the rudimentary block. So even if it is a three-dimensional object that you're seeing in your computer, it's a technique of projection mapping where you have um, uh, where each edge of a three-dimensional object is broken down into small little triangles. And then when you have three edges defined or 3 points defined for anything, and then one surface becomes a combination of many of these triangles that share edges, then you can project that 3D object onto a two-dimensional screen. And that's how you can look at a computer screen but know that there's a depth differentiation there, that you can interact in a 3D environment on your computer, if you have played games and stuff. And the same similar concept with headset and stuff, but it just needs more spatial information associated with it. So the point of this discussion is that in that kind of a framework, you need three very important things. You need to make sure that a network or an architecture is able to understand that um, set of points in its relative and in its projections, instead of where the 2D image already gave you that kind of an axis information the way it came. 3D images do not do that. So you can, there are many ways of capturing 3D point clouds, like LiDAR, or with these kinds of HoloLens like tools. You can actually capture and save 3D point clouds. Any kind of training, like design software like CAD like softwares can give you save files in point cloud formats. So there are many kinds of applications like that for it. And so the network would have to be designed such that it understands these point clouds in its relative projections, and not just from just the coordinates itself. So in a 3D image, you have a point which is an XYZ coordinate. So the beginning, your point of that data set is a XYZ. So your it's like how you have RGB, that each pixel is a three-dimensional quantity. You have, firstly, your 3D point cloud is a three-dimensional quantity in its XYZ, and then it has a relative information of distance, of maximum distance, of all those kinds of things. So PointNet is a good architecture, or a archetype architecture that does that. It has a global and a local information feature extraction mechanism that's done through this TNet kind of a network. It does a from a 3 by 3 kind of input data source. It does a projection to a 64 by 64, and then to 1024 2024. And these are just for this particular model, these are the settings, but then can be changed. You can scale up and down those parameters when you're using your own model and training it. But essentially, in this part of the model, you are getting more feature representation of that point cloud, and taking and these blocks are taking things out, like permutation invariance, whether that 3D object is rotated in at a certain angle in 3D space. You do not want the category associated with it to be different. Whether it's a it's same concept, whether something is black or white or in color, you do not want that object to be detected in wrong. So permutation invariance, whether your point of x 0th feature is the rightmost corner or the topmost corner, those things should not matter for your final objective. So then localization, it will perform a kind of a grid. It will break down this image into certain subgrids, and then it will embed how these subgrids are associated with each other. And then it will also do a point by point feature embedding, and it uses things like symmetric functions that do not care about um, the orientation of things. So commutative functions like sum, whether it's a plus b or b plus a, the outcome of it is same. So it can do multiple of these operations on a set of points, and so it will come up with these representations that do not change, for that set of things, to say that now this is invariant to any of those different considerations. So that TNet part does that feature embedding of a 3D object in that kind of sense, where it extracts and embeds information, removing all of those constraints. And then the segmentation network learns how to map those point features to a output classification, or whatever that objective may be. So we're gonna look at this example of a point net, and we'll also look at 3D CNN. So here this is the, and so these are all the tutorials and collab links. So if you want to run this in collab, you can do that. Here this is the data set, you can download that, um, and you can see this is um, a 3D object of a chair. So this original data set might have had a bunch of different classes, but we are going to consider these classes only: bathtub, bed, chair, nightstand, table, and these essentially come from these different 3D like phone like AR applications. There's a lot of use for this kind of data set there. You might have seen AR applications where that puts furniture in a scene, and that sort of thing. So that's why these kinds of point clouds have been studied a lot. And so you, similarly to before, you augment that kind of a data set. For 3D images, jitter is a kind of an algorithm for augmenting data sets. You also have things like so jitter is pretty much same as saying rotation and adding Gaussian noise to images, things like that, but only in terms of that it in a 3D space, jitter would be a spatial or a 3D matrix multiplication construct than a 2D one. So you have to add noise to your data, you have to add permutations of rotations and flips and things like that for to get good kind of performance there. um, then you have a different kind of regularizations. So here a lot of the basic concepts remain same: batch normalization, convolution networks, you can activations of ReLU. None of much of these things change, but regularizations, those kind of things kind of have to be different. Or if you have like a convolution neural network, like here you'd probably be using something like uh, a 3D equivalent CNN operation. So this article explains that, well, so this was your 2D, this was your image, this was your convolution filter, and so you did a max pooling there, but in a 3D you would have different permutations of those 3D dimensions. So you could pick the XY coordinates and make a matrix, and then Y and Z and make a matrix. So you have different permutations of that, and then each of them can have its own respective filters and have its own corresponding max pool output. So those kinds of considerations change. You have regularizations if you have something like a Gaussian noise or something before that had just a XYZ distribution. Now you may also want to add a different component to it. You may also want to do it in a different way where you project those 3D to a one surface and then add a regularization for that. So there are different techniques in literature. This is what they've used for PointNet. So it's essentially an L2 regularization technique where L2 is a matrix structure invariant operation. So no matter what the dimension of the tensor, you can always take an L2 norm of that. So so this regularization works well for it. So now it's very similar to previous things. You have a call or a forward function where you do the tensor dot, or a matrix multiplication, you reshape that and then you reduce some that through the regularization operation. And so this is a bunch of matrix math that you do not you may not want to like learn completely, but you should be able to use some of these architectures, and there are different libraries now that do this sort of things. But if you have like a data set or a means of collecting 3D data, if you have like a CAD software and you wanted to I don't know, distinguish between three different types of machines, and you could create a data set like that very easily. A lot of people actually have done this for different motors. So you could get point clouds from motors easily from different CAD softwares. There's a lot of data available for that. So that kind of applications, you can get that data and use these pre-trained models and fit that to that kind of a data set or train them from scratch. Um, so here you have pretty much this kind of structure that's defined here. You have to first define a TNet, what a TNet is, and a TNet is essentially this kind of an operation. It does a multi-layer perceptron. It takes all the 64, first all the three dimensions, lines that are up, projects that into a 64 one, and then to a 128 one. So it does a multiple steps of projections using multi-layer perceptrons. So what that means is that it can have multiple layers internally that can themselves have their weights that get trained. Then it does Amax pooling and then a fully connected layer. So this TNet is a complete network in itself that does its own kind of projection objective or a transformation objective internally. So you have to build that, um, and then you build the segmentation network and pass that on. This is you can name your network different things after you have composed it. Um, and so when you train it, these are the kind of outputs that you get. It's not a very accurate model. You can see, because 3D object detection is a very difficult task to begin with. You can see here that these are actually toilets, but labeled as chairs or predicted as chairs. So you can try and see how you can improve on this, give it more data, give it different parameters, train it longer, use different hyperparameters and stuff like that. Now, a 3D CNN, you could also use this data set with this architecture and see if that improves things. So you would have all of that set up here in terms of the data. And so you have this in a point cloud. In this data set, you didn't have RGB values. It was just an XYZ dimensional thing, but you can also have RGB values if it's like a spline kind of a data set, and it's not a point cloud one. And in this data set, this comes from this Kaggle competition. If you go here, you should be able to download that data set from there. So anytime any of these scripts do not have a data set, you go to those links on that notebook, and they should have data like that. So Kaggle standard will have a download link like that, and then you can sign in there with an account. You should have a Kaggle account. And lately Chrome is having a problem with these account sign-ins. So um, anyway, so you can download this file from there, and this is an HDF5 format, which is like, if you have a lot of numerical data, you can store that on your hard disk and read it from disk instead of loading things on a memory. And this is a very efficient way of doing that when you have a large numerical data set. So here you are loading things from that file. um, and transforming it, and then you have to convert um, the labels to have a categorical mapping, um, and so then you convert this to the correct format of labels and create a data loader for it, have a batch size, all of the standard stuff that we talked about. Then for CNN layers, you have to make sure that it's a 3D CNN layer. It has those three channels. Then it similarly you have passing through a convolutional network. You pass your data through a convolution layer one, convolution layer two. Then you unfold that matrix that's learned to a um, linear layer through a view function. And so we have talked about this before. To go to a final prediction that is 10 classes, you need before that transformations that can map it to those 10 neurons, or whatever. If you had 5 neurons, you would need a previous layer that can bring out those 5 layers, or 5 neuron connections. So from a convolution neural network, you have to perform at some point a unfolding operation, or an unsqueeze operation, which is this view function. Here at this point, you have actually taken a reduced feature map of an image to a list, and then you send that through a fully connected, and same ReLU activation. You can drop weights, and this is a regularization technique, and then the final output layer that will have the classes that you define. Um, so same thing, number of epochs, cross entropy loss, SGD. None of this changes very much. So one thing is that this is not a very specialized network for something. So you can try using the point cloud, and try and see if this will actually say, instead of this RGB, can you use the XYZ point cloud information, and what the accuracy looks like if you did that. Because it's just all learning feature representations, and then if you did that, you would actually see the problem that some of these blogs and stuff and paper talked about, why a point cloud data set and doing this kind of a thing is different from the usual thing. Um, yeah, same number of epochs, freeze the network, update the loss, or calculate the loss, update the weights, get the accuracy till satisfactory loss or number of iterations. Um, okay. This is also an application for video processing, and we are going to look at how to either take 3D images, or take a video feed from a phone and try to build an application around that next week. So this is just an example to try out, and these are all collabs. You can in the presentation, I have given more slide information there. They have more breakdown of why we do this and frame by frame. You can represent a video processing application as a CNN plus RNN kind of a task, where first one image is like one word with its own feature embedding through a CNN network, and then multiple CNN networks can form a larger RNN network that captures that sequential information. So there are many different techniques that have been used. Here, what you're doing is a next frame prediction application. So next frame prediction has to be like a has to capture this step information there. So this uses an NSTM construct, but it also has the convolution network to capture the image features and things like that. Um, so you can try running that. seeing the different embedding dimensions and how they change through the network, and then try running it. We are gonna try and see more applications of this next week. Okay, so we have 5 minutes, and so this is like just a very broad overview of the kind of current stuff that's going on in general. 3D data and 3D networks have a lot of attention right now. Kind of these image classification operations or applications have benchmarks and have their set development or research cycle. Like every year there are these conferences. Right now there's a CPVR conference that's going on. So every conference, the companies like Google and Facebook come up with new, or different universities come up with new slight modifications to existing architectures or different kinds of techniques to get the accuracy up. And so, if you have a particular task, it's good to keep that sort of development in, keep tabs on it. But then sometimes it also doesn't make a huge difference for, for a very new sort of an application that you may need to build. So going through these things and trying to reuse the network weights and stuff to build something, that's where you would get anything out of learning this stuff. um yeah, and 3D is gonna like develop more and more, and you're gonna have more standard networks for that. Okay, we can answer some questions now. Yeah, so activation functions, it doesn't change very much from what we have talked about standards, and we looked at in the presentation before. There was kind of a theory, or if trial and error kind of outcomes there, that what kind of a loss objective or what kind of a task that you're doing, then what kind of an optimization or activation function that you use. And just ReLU is a good standard like default to go to for internal weights, and then for the final layer, depending on your task, softmax, those kind of things. For some of the 3D or more applications that need regularization a lot, leaky ReLU is a good one to use. A leaky ReLU is same thing. It just has a it's a more let's see if I have an image here for that. So, okay, if this was your ReLU, then your leaky ReLU was like when it was negative, it had a smaller gradient on the other side of the axis. So it wasn't like so much of a hard activation where it was a zero and over there it just started going up. It was slightly progressive. So even if something was negative, so usually you want, there's a bias or something like that, that beyond which you activate a function or activate the neuron. So you just kind of modulating that activation process in a leaky value thing, so that the model is actually less sensitive to the very structures of the input. So if you had an application that was very easy to become biased, had images that had this particular background all the time, or had these kind of very similar looking structures in point clouds and things like that. So those kinds of things that can benefit from more regularization, leaky ReLU is a good one to use. So that's the other one that some of these networks suggest. So am I missing any questions here? Okay, so some of the okay, my chat is kind of freezing, so can if anyone has any question, they can speak out, or they can put it in the Meetup channel or the Slack channel. If anyone wants to be added to the Slack channel, send me your email IDs